This video is on Bayes' theorem, which is following from conditional probability. So sometimes we know the conditional probability of A given that B has occurred, but we want to find the reverse. We want to find the probability that B occurs given that A has occurred. Let's look at an example. Suppose that in a certain course, if you study for a quiz, the probability that you'll get a B or higher is 85%. If you don't study, the probability that you get a B or higher is 30%. And you study for quizzes 90% of the time. So if you got a B or higher on a particular quiz, what is the probability that you studied? To get started, let's again let B be the event of a B or higher. Let's let S be the event of you having studied. And something to keep in mind is just that we know that the probability of A given B in general is the probability of A and B, the probability of both things occurring, divided by the probability that B occurred. And remember that definition of conditional probability, or that formula for it, we just get by taking the multiplication rule. Probability that A occurs and B also occurs is equal to probability of, we can do in either order, B happening times the probability that A happens given that B occurred. And then just taking that equation and dividing both sides by probability of B. So really everything's following from the multiplication rule. Okay, so give that a try. And we'll talk about it in just a moment. Okay, let's think about what we know so far. So we say that if you study for a quiz, the probability that you'll get a B or higher is 85%. In other words, knowing that you studied for a quiz, the probability that you get a B or higher is 0.85. If you don't study, so probability of getting a B or higher given that you have not studied, S complement, is 0.30. And you study for quizzes 90% of the time, so probability of studying is 0.9. So if you get a B or higher on a particular quiz, what is the probability that you studied? So this is all the stuff that we know. And the thing that we want to find is, given that you got a B or higher, what is the probability that you studied? So we know that that's equal to the probability of both S and B being true divided by the probability of B. That's just the regular formula we have for conditional probability. And now let's think about each of these pieces individually. So this is equal in the numerator to the probability of S times the probability of B given S. So that's just the multiplication rule. And we're trying to write this all in terms of things that we already know about. So we do know probability of S, we do know probability of B given S, divided by probability of B. So in the last video, we saw that one way we can think about this is dividing up the event B into either the event B happens after we studied for the quiz, or the event B happens after we did not study for the quiz. So this is the probability of S and B, or plus the probability of S complement and B. And so that would be equal to the probability that we studied times the probability that we got a B given that we studied, divided by the probability of S and B. That's probability that we studied times probability that we got a B given that we had studied, plus, again using the multiplication rule, the probability that we didn't study times the probability that we got a B despite not having studied. And now plugging in the values that we know. So we said that we study 90% of the time, 0.9. And when we study getting a B, there's an 85% chance of that, divided by the probability that we studied, 0.9, times the probability of getting a B after studying, plus the probability that we didn't study. So if we study 90% of the time, we don't study 10% of the time, times the probability that we get a B despite not studying, 0.3. And now we just need to plug that into a calculator or whatever, and we get 0.962. So the probability that we get a B on a quiz, the probability that we have studied, given that we got a B on the quiz, a B or higher on the quiz, is 96.2%. So we just completed that problem using a bunch of basic rules together, the multiplication rule, the idea of mutually exclusive events and adding them together, and the definition of conditional probability. So basically, using all of that, we essentially on our own figured out Bayes' theorem, which is the following. It's written in different ways. One of those is that the probability of A given B is equal to the probability of A times the probability of B given A divided by probability of B. That's one way that people write Bayes' theorem. Another way that people write Bayes' theorem is to expand that out a little bit more and to say that the probability of A given B is equal to the probability of A times the probability of B given A divided by, so in the special case that we're just talking about, A occurring or A not occurring, then it would be probability of A times probability of B given A plus the probability of A complement times the probability of B given A complement. So just expanding out one way of describing the probability of B. This is basically the probability that A occurs and B occurs plus the probability that A doesn't occur and B occurs, which we know is equal to the probability of B. And finally, one more way of writing it is below. And so this is a more general form when we're not talking about just splitting A up into two events, either A or not A, but splitting up into, the first variable can have K different outcomes, and those outcomes are A1, A2, ... up through AK. So this is exactly the same formula below, just expanding out the probability of B in a more general sense. Let's do another example together. Suppose that 1% of people have a certain genetic disorder. There is a test for this disorder, but it is not always accurate. The probability that the test gives a false positive is 10%, and the probability that the test gives a false negative is 8%. If an individual gets a positive test result, what is the probability that they actually have the genetic disorder? Let's use the same names for events just so we have our same notation. So let's let T be gets positive test result. And let's say that D is the person has the genetic disorder. So to start off, I'd like you to just write a few of these events as conditional in conditional notation. So the probability of a false positive, the probability of a false negative, and if an individual gets a positive test result, what is the probability they actually have the genetic disorder? So write all of these things as statements using the notation of conditional probabilities. And after that, you can also try to start to solve the problem. If an individual gets a positive test result, what is the probability that they actually have this genetic disorder? So I'm actually going to pause twice. I'm going to pause once and just write these out. And then I'm going to pause a second time and solve the problem. Okay, so to think about just writing this notation out. So what does a false negative mean? So false negative, the probability of a false negative. What is that? That's the probability that, so what do we know? If it's, false negative, we're writing first. Okay, false negative. That's the probability that the test result is negative, T complement, given that if it's a false negative, that means that the person actually does have the genetic disorder. So this is how we would write that with conditional probability. The probability of a false negative is equivalent to the probability that the subject has a negative test result, given that, with the truth that the person does actually have the genetic disorder, whereas the probability of a false positive, that's equivalent to the probability that, so false positive, that means that the person did have a positive test result, but the person does not, in truth, have that genetic disorder. So that's the probability that they get a positive test, given that they did not truly have the disorder. And finally, last one, if an individual gets a positive test result, what is the probability that they actually have the genetic disorder? So the thing that we're trying to find is if the individual gets a positive test result. So given that the individual gets a positive test result, what is the probability that they actually have this genetic disorder? What is the probability of D? So those are each of those things written as conditional probabilities. And so we are trying to find the probability of D given T, and we can use Bayes' theorem to do that. So go ahead and pause again and try this out. Okay, we'll again break up into the things that we know. So we know that the probability of false negative is the probability that we get a negative test result despite having the genetic disorder, and the probability of a false negative is 8%, so 0.08. The probability of a false positive is the probability that we have a positive test result despite the fact that the subject does not have a genetic disorder, and so that's 0.1. And what else do we have? We have the probability that somebody has the disorder in general. The likelihood of that is 0.01. So those are all the things that we know. And now let's think about the things that we are trying to find. So we want to find the probability that if an individual gets a positive test result, so given that they've had a positive test result, what's the probability that they actually have this genetic disorder? And we know that that is equal to the probability of that they do have the disorder and they have a positive test result divided by the probability that they have the positive result. So again, I'm just using the formula for conditional probability. And so that is equal to the probability that they have the disorder times the probability that they get a positive test result given that they have this disorder divided by the different ways that they could get a positive test result. And there's two ways for that to happen. Either they get a positive test result because they had the disorder, or they get a positive test result and they did not have the disorder. So either they have the disorder and they got a positive test result, or they do not have the disorder and they got a positive test result. Those are the two different ways that they could get a positive test result. So then that is equal to the probability that they do have this disorder is 0.01. The probability that they get a positive test result given that they have this disorder. Well, we actually don't have that, but we do have this probability, which is the complement of what we're interested in. If given that the individual has this disorder, either they get a positive test result or they do not. So this is the complement of the event we're interested in, and so this is 0.92 divided by 0.01 times 0.92, same thing again, plus probability they do not have the disorder, 0.99 is that probability, because the probability of having the disorder is 0.01, so it's the complement of that event, times the probability that they get a positive test result despite not having the disorder, so that is 0.1 up here. Okay, so now we just need to plug all those values in, and when we do, we'll get 0.085. So this is saying that even though the individual has received a positive test, there's less than a 10% chance that they actually have this disorder. And that's not especially uncommon, especially for, rare diseases or disorders, say cancer screenings. So in a lot of situations like that, if someone gets a positive result, the person giving the test will actually order future tests because even though these false positive, false negative rates weren't that high, 10% false positives, 8% false negatives, despite that fact, the probability that your test result is accurate if you get a positive test result in this case is less than 10%. And this wasn't even that rare of a disorder, so 1% of people, that's not especially rare. There are many disorders or diseases or whatever that people get tested for that have a much lower probability